sequence notation can be a little confusing until you practice with it. So I want to show you examples of two recursive sequences and two explicit rules for sequences and how we use them to generate the terms in the sequence. So we'll start out with two recursive rules. We can recognize these as recursive rules because they both refer back to a previous term. We see an a sub n and we see an a sub n minus 1. Here we see an a sub n, an a sub n minus 2, and an a sub n minus 1. So it's referring back to previous terms in the sequence. The two sequences down here are both explicit rules. And the way we know these are explicit rules is you notice that everything in the formula is just, the only variable in the formula is n. N tells it, n, we know what to do with the sequence because we put the n in for the term number, and it ever refers back to a previous term. There's no a sub n minus 1. So when we work with a recursive sequence, we start by listing any given sequence term. So we start out with a sub 1 equals negative 3. So we have our first term. For n equals n greater than or equal to 2, then we start using the formula. So we start out with a sub 2 is equal to, and now substitute a 2 everywhere there is an n. A sub 2 minus 1 times 2. Well, a sub 2 minus 1 is a sub 1 times 2. Well, what's a sub 1? 3, negative 3. So negative 3 times 2 is negative 6. So there's the second term in the sequence. So here's the first term, there's the second term. Now to get to the third term, a sub 3, now put a 3 every place there's an n. So a sub 3 minus 1 times 3 equals a sub 2 times 3. Okay, well I know what a sub 2 is, I just calculated that. A sub 2 is negative 6, so I'm going to substitute that in. Negative 6 times 3 is negative 18. So there's the third term in the sequence. So now I think you see what's going on. And each time I'm taking the previous term and then multiplying it by the term number. So a sub 4 is going to be a sub 4 minus 1, which is a sub 3 times 4. A sub 3 is this previous number that I've gotten here. That's negative 18. Negative 18 times 4 turns out to be negative 72. And then to get a sub 5, that's going to be a sub 4 times 5. So take 72, put it in there, and I have negative 72 times 5, which turns out to be negative 360. So the first 5 terms in my sequence are negative 3, negative 6, negative 18, negative 72, negative 360. And just homework tip, if I ask you to do this on homework or on a test, I want to see some work. I don't want you to just do all of this in your calculator and write down the numbers. Okay, I want to see that you actually understand how to use the sequence notation by showing me. So make sure to at least write down all of the steps in a couple of the examples. Then once you see the pattern, you don't have to write down quite as much after that. Okay, so the second one. A sub 1 equals 2 and a sub 2 equals 2. So I've been given the first two terms in the sequence. That must mean that my rule refers 2 terms back. So for n equals 3, so now I just have to calculate for 3, 4, and 5. A sub 3, so every place there's an n, I'm going to put a 3. A sub 3 minus 2 over a sub 3 minus 1, which is a sub 1 over a sub 2. I want you to notice that every time we use a subscript, that subscript is not an operation like that we multiply or add or do anything to a number. All it tells us is a term, a position in the sequence. So it just identifies which term we're looking for. So a sub 1 is 2 and a sub 2 is 2, so this is 2 over 2, which is 1. So first 3 terms in the sequence are 2, 2, and 1. A sub 4 then is a sub 4 minus 2 over a sub 4 minus 1, which is a sub 2 over a sub 3. Well, a sub 2 is 2, a sub 3 is 1, 2 over 1 is 2. So there's the fourth term in my sequence. Fifth term. Well, notice that we did a sub 1 over 2, a sub 2 over a sub 3, so this one's going to be a sub 3 over a sub 4. A sub 3 is 1, a sub 4 is 2, so the last term in my sequence is 1/2, or the fifth term. Okay, now when we go deal with an explicit rule, now I don't start out being given any terms, so I just have to start out with starting with 1. A sub 1, put a 1 every place there's an n. -1 to the first, 1 squared plus 1. -1 to the first is -1. 1 squared plus 1 is 2. So my term is -2. A sub 2 is -1 squared times 2 squared plus 1. Notice I don't ever go back and use my previous term. I don't do that at all. I just put the term number in. So -1 squared is a positive 1 now, times 5. So this is a positive 5. A sub 3, -1 cubed times 3 squared plus 1, which is -1 times 10, or -10. Notice that when I raise -1 to an odd power, I get a -1, but when I raise it to an even power, I'm going to get a positive 1. So my terms are going to alternate signs between negative, positive, negative. The next one will be positive because I will be raising -1 to the 4th power, which is a positive 1. Then this would be 4 squared plus 1. So this would be 1 times 17, or 17. And the last one is going to be negative again, -1 to the 5th times 5 squared plus 1, -1 times 26, -26. Last example, also an explicit rule. So a to the 1 is 1 plus 3 over 1 minus 2, which is 4 over -1, or -4. A sub 2 then would equal 2 plus 3 over 2 minus 2, which is 5 over 0. So I actually got an undefined term in my sequence. I'm not really sure if that is a legitimate sequence, but we'll just go with it. I kind of made this rule up yesterday, and that's what I ended up with. A sub 3 then is going to be 3 plus 3 over 3 minus 2, which is 6 over 1, which is 6. A sub 4 then, 4 plus 3 over 4 minus 2, which is 7 over 2. That's my next one. And a sub 5 is 5 plus 3 over 5 minus 2, which is 8 over 3. So you notice you have 4 over -1, 5 over 0, 6 over 1, 7 over 2, 8 over 3. The next one's going to be 9 over 4. Okay, it's just going to keep following that same pattern. So here are my 5 terms from this sequence. I could go, now what's the big difference between explicit and recursive? If I wanted to find the 100th term here, I would have to say a sub 100 is equal to a sub 98 over a sub 99. I would have to know terms number 98 and 99 in order to find term number 100. That means I would have to find all of the terms one at a time, going all the way up to 100 in order to use this rule. So a computer could do that really quickly. You could program a computer to just keep just churning through this rule over and over and over. Recursion is used in technology all the time because technology doesn't mind being repetitive. As a matter of fact, technology is very good at being repetitive. So we can just repeat the same process over and over and over. But if I want to find the 100th term here, all I have to do is say a sub 100 is 103 divided by 98. I can go straight to it. I don't need to know the 99th term. I just can go straight to the whatever term I want. So that's the main difference between explicit rules and recursive rules. Recursive rules are great for technology. They're great for generating the first few terms. Explicit rules are better if you want to go specifically to any term in the sequence. Notice that none of these sequences are arithmetic or geometric. They're just kind of different sequences. I mean, they all have their own little pattern, but none of them are arithmetic or geometric. So just because something has a pattern doesn't mean it fits in one of the categories that we looked at. There are many, many sequences with patterns that aren't arithmetic or geometric.